Picture this. You are walking up to the entrance of a highly secure, top-secret facility.
Okay, I'm picturing it.
You've got your visitor badge on a lanyard, and you walk up to the security guard. And this guard is, like, meticulous. I mean,
Yeah.
they are intensely inspecting your badge.
Right, doing their job.
Exactly. They check to make sure the plastic lamination is exactly the right thickness. They pull out a magnifying glass to confirm the font used for your name is standard issue.
Wow.
Yeah, they even check if the barcode is printed at the exact right angle. And, if the holographic foil reflects the correct wavelength of light.
So it's the illusion of an incredibly thorough security check, right? But they're focusing entirely on the physical characteristics of the credential.
Yes. They give you a crisp nod, a green light flashes, and they open the heavy steel door for you.
Yeah.
But there is just one tiny, terrifying problem here.
What's that?
That guard completely failed to look at your face to see if it actually matches the photo on the badge.
Ah. Yeah, so you have a defensive system that is flawlessly executing the wrong checks, which creates a massive false sense of security.
Welcome to another deep dive. Because today we are looking at how the digital infrastructure you and I trust every single day might be guarded by that exact same fundamentally blind watchman.
It's a huge issue.
It really is.
Yeah.
We're looking at this fascinating article from AI 365, published on June 9, 2026. It's called The Gateway Mirage: Why Standard API Security Scans Miss Broken Object-Level Authorization Anomalies.
The implications outlined in this piece are just staggering. I mean, our mission today is to uncover exactly why relying on standard automated AI scanners for application security is leaving massive amounts of enterprise data totally exposed to the public.
Right.
And more importantly, we are going to detail the specific protocol engineering teams need to implement to stop it.
Because right now, the dashboard might be flashing a flawless green, but the front door is wide open.
Yeah, wide open.
But before we get into the mechanics of how these automated AI scanners are failing so spectacularly, we need to look at, the pressure cooker environments that force engineering teams to rely on them in the first place. Like, why is the Watchman just a generic AI script?
Well, it comes down to sheer velocity.
Velocity.
Okay. The modern application backend is a highly complex web of microservices. Organizations are in a dead sprint to connect internal databases to external customer portals and mobile applications.
Right. Everyone wants everything instantly connected.
Exactly. So the speed of API deployment has completely outpaced traditional security monitoring. We are talking about enterprise applications exposing thousands of new endpoints to the public internet every single week.
Thousands. A week.
Yes. Human security engineers literally cannot review code that fast. It's impossible.
So to keep up with this frantic release cadence, this whole CI/CD pipeline thing, engineering teams have started outsourcing their AppSec to AI.
That's the workaround they found.
You have a machine writing the code, and you have a machine checking the code.
Right. What they do is they feed an open API or Swagger schema, which is basically the architectural blueprint of the API into a large language model.
Okay.
And they give it a generic open-ended prompt, something like, audit these API endpoints for potential security vulnerabilities and flaws.
And the AI spits back a glowing review, right? The system gets a passing grade.
Yeah, basically every time.
Because the AI catches basic signature-based syntax errors. It flags if you forgot to enforce HTTPS, or if you have an outdated CORS policy, or if your error messages are leaking stack traces.
All the structural stuff.
Right. So the dashboard lights up green. The team pushes the code to production,
leaving the application wide open to exploitation, all while the engineering team believes they are fully protected.
Okay, let's unpack this for a second because I'm struggling with something here.
Sure.
We're in 2026. If these models are complex enough to architect entire microservices from scratch, why are they failing at a basic security review?
That's a great question.
To me, it sounds like using AI as a basic spell checker. Like, it's reading a novel and saying, oh, all the words are spelled correctly, the grammar is perfect, but it completely ignores the fact that the actual plot of the novel makes absolutely no sense.
That is a perfect analogy.
Right. It checks the grammar of the code, but ignores the actual meaning or consequence of the instructions.
Yeah, that spell checker analogy perfectly captures what the article calls the syntax-only delusion.
The syntax-only delusion.
Exactly. We have to look at how LLMs actually process information under the hood. They are fundamentally predictive text engines that analyze stateless snapshots of code.
Stateless snapshots, so it's not live.
Right. When an LLM evaluates your schema, it evaluates it in a vacuum. It reads a sequence of tokens and statistically correlates a function like, say, require auth with the concept of secure.
So it's doing advanced pattern matching, not actual logic execution.
Exactly. The AI does not instantiate a database. It doesn't spin up a mock server and run stateful user sessions.
It's just reading the blueprint.
Yes. And because the schema doesn't actively run in an environment during the scan, the AI is mathematically blind to the contextual overlap between different users.
Oh, okay.
It confuses schema compliance with behavioral security. An endpoint pattern can match your documentation perfectly and compile without a single warning. The grammar, as you said, is flawless.
But logically,
Logically, behaviorally, it can still serve as an open conduit for massive data extraction.
which leads directly into the first major architectural blind spot the article identifies, which is the contextual authorization gap.
Right.
Imagine the AI reads an endpoint, something like a PIV1 data. The AI looks at it and confirms this endpoint requires a valid authentication token to be accessed. Green light.
But because it's a stateless check, it completely fails to test the access control list logic.
Meaning what, exactly?
Meaning it checks if a token is present and cryptographically valid, but it doesn't test the boundary of that token. It misses the critical vulnerability of whether a token belonging to user A can be maliciously used to fetch data belonging to user B.
Oh.
Yeah, it lacks stateful context.
So the AI can't tell if my key opens your door.
Exactly.
But what if I don't just try to open your door? What if I try to tell the system I own the whole building? Does the AI catch that?
And that brings us to the second massive vulnerability, parameter mass assignment blindness.
Here's where it gets really interesting.
Yeah.
Because the way this works is almost comical if it weren't so dangerous.
Yeah, it's wild.
It's like walking up to the front desk of a hotel, filling out a standard registration card, but you decide to just scribble in at the bottom, P.S. I am the general manager now.
Yeah.
And the hotel's computer system just reads it and says, oh, okay, here are the master keys.
The mechanism behind that is a failure in database mapping boundaries.
Okay, break that down for us.
Well, the AI checks if a standard POST request handles the intended data inputs, like a name and an email address. It validates the schema structure, but it misses the danger of hidden injected parameters.
So an attacker just appends, like Eisdenman, true into the JSON body of their request.
Exactly. And because the system wasn't explicitly told to reject that unprompted input, and the AI only verified the structural layout of the intended request, the database just accepts the payload.
It just upgrades their user privileges.
Yes.
Huh.
The AI scanner never asks, what happens if a user submits a field that isn't in the schema?
That's terrifying. And, you know, if I can get admin access just by asking nicely, what happens if I ask for a massive amount of data repeatedly?
It's the same blind spot.
Because it seems like if the AI is blind to mass assignment, it's probably missing volume constraints too.
It absolutely is, which is the third blind spot, the rate limitation omission.
Right.
The AI verifies the layout of a high-volume data fetching endpoint. Structurally, it looks perfectly standard,
All right.
but it ignores the absence of rate-limiting policies or payload size constraints.
So it doesn't simulate the operational physics of the endpoint.
Exactly. It doesn't ask, what happens if someone hits this endpoint a million times a second? By missing that, the backend is left entirely exposed to systemic automated data scraping and denial of service attacks.
Okay, so we have these massive architectural blind spots. The AI checks the syntax, but it doesn't check if my key opens your door. It lets me promote myself to admin, and it will gladly serve me the entire database a million times a second if I request it.
That sums it up.
To really understand the stakes here for you, the listener, we need to map these abstract vulnerabilities to real-world application environments. We need to talk about BOLA.
Yes. Broken object level authorization. This is the core threat in modern software architecture today.
BULA.
Right. This is the real-world exploitation of that contextual authorization gap we just discussed. Even if an endpoint pattern matches the documentation perfectly, if it has a BOLA vulnerability, your application perimeter is fundamentally breached.
Let's look at a very common endpoint from the source material. It's a PIV1 user's profile.
Okay, classic endpoint.
The AI scanner looked at this and validated that the incoming token is cryptographically signed. But the system only checks that you are a valid logged-in user. It doesn't check who you are asking about.
That's the difference between authentication and authorization.
Right.
Authentication confirms you are who you say you are. Authorization dictates what you're allowed to do.
And the AI missed the authorization part.
Completely. The AI verified authentication, but completely glossed over object-level authorization. So an authenticated user, any user with a standard account, can just go to that URL.
Let's say their profile is V1's users 1001.
Right. They just change that integer in the URL to 1002
Literally just typing a 2 instead of a 1.
and press enter. And because the backend doesn't cross-reference, the object requested user 1002 with the token of the person requesting it, user 1001, the server just hands over the data.
That's wild.
Yeah.
So the attacker writes a simple Python script to iterate that ID sequentially. 1001, 1002, 1003, all the way up to 1,000,000.
Yep.
And they systematically scrape the full name, physical address, and billing data of every single user in your database.
And the craziest part is, because they are using a valid cryptographically signed token, the system never triggers an authentication failure alert. The dashboard stays green the entire time the data is walking out the door. It is a completely silent data heist.
That's the scraping side. But the article also outlines a second real-world scenario that made me stop and actually reread the paragraph. Data exposure leaks.
Right.
The article describes a vulnerability where the response payload from the backend maps the entire user database table layout directly to the client interface.
Yeah, this ties back into the velocity problem we were talking about earlier and how modern applications are built.
Oh, wait, I have to ask, why would an application ever send a password hash or a two-factor secret to the front end if the screen is only designed to show, like, a cartoon avatar and a nickname?
It seems crazy, right?
I mean, structurally, why would a developer even write it that way? It makes no sense.
Well, it happens because of the friction involved in writing data transfer objects, or DTOs, combined with a heavy reliance on unconstrained ORM's object relational mapping tools.
Okay, so it's a tooling issue.
And a time issue. Developers are under intense pressure to build fast. Writing custom serialization logic for every single endpoint, explicitly detailing only pull the avatar and nickname from the database, is tedious boilerplate work.
It slows down the sprint.
Tremendously. So instead, they use a shortcut. They tell the ORM to just fetch the entire user object, select all.
Just grab everything.
Right. The backend grabs the entire row from the database, including the password hashes, the internal tracking GUIDs, the secret keys, and throws the whole package over the network to the front end.
Wow.
And they rely on the front end code, the user's browser, to filter out what it shouldn't display.
So the browser gets the secret key, but the website's code says, hey, don't draw this on the screen, just draw the avatar.
Exactly.
But anyone who opens a network tab in their developer tools can see the raw data packet in plain text.
Anyone.
And the AI scanner missed this because, structurally, the endpoint successfully fetched the user profile just like the schema said it should.
The AI doesn't understand that the contents of that envelope shouldn't be traveling across the network. It assumes the abstraction layer is handling the security.
So we have AI giving the thumbs up, while sequential scraping and mass data exposure are literally baked into the code.
Yep.
Since simply asking an AI to audit this results in a breached application masquerading as a green dashboard, engineering teams clearly have to radically change how they use these automated scanners.
It requires a massive mindset shift.
What does that look like?
Well, true API security isn't about confirming that an endpoint exists or that it compiles. It is about actively proving that the endpoint cannot be subverted. We have to stop allowing AI models to run these passive descriptive reading checks.
The article proposes a solution they call the perimeter gatekeeper protocol.
Right. The core idea here is that you must set up the environment before the AI even looks at the code. Teams must inject explicit enterprise security baselines, access control policies, and data boundaries into the AI's prompt before running the security sprint. You don't just say, audit this. You give the AI the complete context of your business logic.
Okay, let's unpack this for a second.
Yeah.
Because I have a major issue with this approach.
Get me.
Isn't writing explicit rules for the AI exactly what we were trying to avoid by using AI in the first place?
It's a fair point.
If developers have to write all the access control logic manually to feed to the prompt saying, user A can't see user B, no one can self-promote to admin, haven't we just defeated the entire purpose of automation?
You'd think so, yeah.
If I have to spend hours writing the rules, I might as well just review the code myself.
It's a completely valid pushback, and it highlights the central tension of modern AppSec right now. But the perimeter gatekeeper protocol isn't asking developers to manually write unit tests for every single endpoint.
Okay.
It is asking for a shift in prompt engineering.
Uh,
You formalize your business logic once a baseline document detailing your authorization boundaries. You feed that baseline to the LLM alongside the OpenAPI schema, and then you change the nature of the prompt.
you make it hostile.
Exactly. You program the AI to act as an adversarial penetration tester.
Oh, I like that.
You instruct it. Here are our absolute business logic constraints. Generate payloads that specifically attempt to violate these rules while still passing basic schema validation. You force the AI to target the execution logic.
So instead of treating AI like a passive spell checker, you treat it like a simulated hacker. You give it the locks and you tell it to pick them.
That's exactly it. And when you constrain the AI with adversarial boundaries, it actually catches the BOA vulnerabilities.
Because it's actively looking for them.
Right. It flags the mass assignment risks because it actively attempts to inject the Eisenman true parameter to see if the schema absorbs it.
That makes total sense.
And once it finds those logical flaws, the article outlines the specific remediation steps required to fix the code itself.
Let's talk about those remediation steps.
Yeah.
Because finding the hole is only half the battle, right? What is the actual architectural fix?
The first major remediation is injecting explicit ownership verification validation middleware.
Okay, so think of middleware as a bouncer that stands between the incoming requests from the internet and your backend database.
Perfect analogy. This specific ownership verification bouncer sits right in the execution stack. Before the controller is ever allowed to query the database, the middleware intercepts the request.
It stops it at the door.
Yes, it extracts the ID from the valid authentication token, and it cross-references that identity with the specific resource being requested.
Okay.
It mathematically forces the system to answer. Does the owner of this token have the legal right to access this specific row in the database?
So it connects the who are you to the what are you allowed to touch.
Exactly.
If user 1001 asks for user 1002's data, the middleware kills the request before it even reaches the database.
The BOA vulnerability is neutralized at the routing layer.
Nice.
Yeah, the second critical remediation step addresses the data exposure leaks we talked about earlier. It requires intercepting payload serialization before the data ever leaves the server environment.
And for context, serialization is basically packaging the data up to send it over the network.
Right. Instead of letting the unconstrained ORM blindly throw the entire database row to the front end, you force the backend to explicitly serialize the data. You implement strict data transfer objects.
DTOs.
Yes. The backend code actively strips out the password hashes, the internal GUIDs, and the two-factor secrets.
So it forces developers to embrace the friction they were trying to avoid in the first place.
It does.
They have to specifically write the code that says, only pack the avatar and the nickname into the network packet. The secret data never leaves the vault.
That is how you secure an endpoint. By injecting explicit logic constraints, not just checking the syntax layout, you force the server to be the ultimate source of truth for both authorization and data filtering.
This is such a critical shift in perspective, tying all of this technical deep dive insight back to you, the listener, and your day-to-day interactions with technology. What we've learned today is that an interface is truly only as secure as its weakest logic path.
Absolutely. Relying on generic automated stands that just check schema layouts without aggressively cross-examining the authorization architecture leaves the application data perimeter entirely undefended.
It's a security theater.
It is. The tools we use to defend our networks are fundamentally misunderstanding the nature of the threat. They are looking for typos while attackers are exploiting logic.
Whether you are an engineer pushing code late on a Friday, a manager overseeing a massive tech stack, or just a user whose personal data is floating out there in these databases, you need to know this.
Everyone needs to be aware.
Object authorization paths must be actively locked down. Input boundaries must be secured before the next production push. You cannot just trust a green dashboard.
You really can't.
Which brings me to a final thought I want to leave you with, something to chew on as you look at the apps on your phone or the portals you log into for work. We know that our current defensive AI scanners are easily tricked by standard syntax compliance.
We do.
We know they are mathematically blind to massive logical holes like BOL, letting data just walk out the door sequentially.
Right.
So, what happens when malicious actors start using their own adversarial AI?
Oh, that's a scary thought.
What happens when the bad guys build models that don't just passively scan for typos, but actively systematically hunt for these specific logical vulnerabilities at scale faster than our dashboards can even load? It's time we start looking at the faces, not just the badges. Thanks for joining us on this deep dive.